Okay, so I'm going to talk about synchronization of cavity laser solitons. So what is a soliton? So first of all, this is a wave which travels without changing shape. So this kind of wave has been first observed back in 1834 by John Scott Russell. So he was observing a boat in a canal, and when suddenly the boat stopped and all the water accumulated at the front of the boat just formed a wave, and he followed that wave for a couple of miles until he lost sight of it. But he observed that the wave just kept the same shape over miles. So, and by this time he called that a wave of translation. So the picture shows the reproduction of what John Scott Russell saw back in 1834. Has been done in Scotland in 1995. So in order to observe cavity solitons, we need to work with semiconductor lasers. So how does it work? Basically, you've got a valence band and a connection band. So the connection band is full of holes, whereas the valence band is full of electrons. So by pumping the device, you can raise the electrons from the valence band up to the connection band, leaving holes behind them. So that means that they can recombine with holes in the valence bands, then creating a photon with an energy corresponding to the band gap. So I use a particular type of semiconductor which is called a VCSEL. So first of all, how does a laser work? So you need to have a cavity. So this is basically a pair of mirrors. One is highly reflective, the other one is only 99.5%. So that means that the amplification can build up within the cavity. And so yes, the VCSEL is a, as I said, particular type of semiconductors. So the emission is perpendicular to the gain region. That means that the shape of the emission can be basically any kind of shape. So here we work with a circular aperture. So how do we obtain cavity solitons? So within a medium, light will experience diffraction. So that's the dashed line, the black lines. So yes, the light will diffract. But if we use a nonlinear medium, then Gale-Lens focusing comes into play. So that basically the refractive index of the medium then depends on the intensity of the light. So therefore the medium can act as a lens, and if you can somehow balance these two effects, then you obtain a wave which travels without changing shape. But within the medium you've got losses, so you need to compensate these losses by placing your nonlinear gain region within the cavity as shown before. So a few properties now. So on the left hand side, so it shows you that the solitons are bistable. That means you've got two stable solutions for the same input intensity. So that means you can switch them on and off using the same input power. And on the right hand side you've got a couple of dots numbered. So they're all solitons, but they are also independent, so that means they show up at different currents. So soliton number 1 shows up between number 8 and so on. And so the aim of this project is to see how they interact with each other. What do they do when they are brought close to each other? How do they interact? So that's basically the aim of this project.